So we worked with this problem last time. It was problem number 14, section 2.7, and it was the height of an object thrown from the surface of Mars, and that height, its position, is given by this function. H of t is 10t minus 1.86t squared, and the problem was to find the instantaneous velocity at a particular time. So that instantaneous velocity is going to be given by the slope of the tangent line. So it's actually this one that I want to find. Now, the other day we found the slope of the tangent line at t equals 1. So, okay, what do we have to do? We found h of 1 plus h, and then we subtracted those two things. It was a lot of work. Brought us all the way down to here. Now, when you subtracted those two things, you saw these things cancel out. We got this nice expression. So that's the change in the heights of these two things. And then we took those two heights, the change in the height, and divided by the change in the width, that is delta y divided by delta x. And we got this ratio, which is the slope. And then we said, all right, well, we're going to take and let that get really, really small. We're going to let h get really, really small so that we're finding the slope of the secant line over smaller and smaller intervals. You take that limit, and we got 6.28 units would be meters per second. Okay, that was a lot of work. And unfortunately, if I then said, okay, hey, you know what? I made a mistake. I want you to find the slope of the tangent line at h equal 2. Then you're like, you give me a big sigh, you roll your eyes towards the ceiling, like, you realize I got to do this all over again. And that's kind of a pain, right? I mean, every time I want to do this, I'd have to do this process all over again. So what we're going to do is we're just going to do it once in kind of a general way, and then be able to get the slope of the tangent line at any point that we want. So we're going to come up with a function that's derived from our function. It's called the derivative, and that derivative function is what's going to measure the slope of the tangent line. So part B for this question that we didn't cover the other day, part B says find the instantaneous velocity at time equal a. Instantaneous velocity at time equal a. So we're going to do this kind of in general and do it once and then be kind of done with it. So what's that going to look like for us? Well, there's going to be a few steps that we're going to have to do. The first one is to find h of a. Find h of a and h of a plus h. So I want to find both of these. And just to remind you, the function itself is h of t equals 10t minus 1.86 t squared. So h of a is the easy part. The easy part is just saying, okay, well, I'll put in an a wherever I see a t. So that's 10a minus 1.86 a squared. Okay. Well, let's keep going. Let's find h of a plus h. So wherever there's a t, I'm going to plug in a plus h. Not bad, but you're going to have to clean this up. We're going to have to simplify this and expand it. So here, I'll distribute the 10a plus 10h minus 1.86. And hopefully when you square this, you don't get a squared plus h squared. What's the real thing here? Come on, make me look at this. This is going out live. Thank you. A squared plus 2ah plus h squared. And now I'll distribute that and get my final expression here. 10a plus 10h minus 1.86 a squared minus 3.72 ah minus 1.86 h squared. Wow, so a lot of work to get that second part, but that's okay. We're where we want to be. Let me kind of explain to you how it is that we're going to find the slope of the tangent line in general for something like this. So here's my function. Its graph is going to be a parabola. And we're going to find the height of this function at some point, call it a. And so the coordinates here would be f of a. And then someplace a little bit to the right of this, maybe, a distance h away. This point is going to be f of a plus h. And basically what I want to do is I want to find the slope of the secant line between these 2 points. You don't have to copy this down. I'm just trying to explain to you what's going on. So there we go. Now how do you find the slope of a line? Well, this line has coordinates, these 2 points have coordinates of a and f of a. And over here, a plus h and f of a plus h. So that's going to be the coordinates. You can find the slope of the line just like you would in any case. It's going to be the difference in the y coordinates. So it's going to be f of a plus h minus f of a divided by a plus h minus a. Now I get a little simplification in this. Do you see where it is? Yeah, the a cancels out in the denominator. So I just get this expression. And if I let the value of h get really, really small, take the limit as h approaches 0, then that secant line is eventually going to become the tangent line, or the slope of the secant line will eventually become the slope of the tangent line when you take the limit. And that's what we're looking for, is the slope of the tangent line. So let's turn back to the calculation. All I did was I found my f of a and f of a plus h. Now I got to subtract them. So I got to find that difference here. The difference between these two, I'm going to call that delta y, is that difference, the change in the height. This difference, delta x, for us, the change in x's, is just going to be h. So let's find the difference in the y's. So delta y is going to be this, h of a plus h minus h of a. So it's going to be this whole big expression here. Well, let me copy that down below. It's going to be 10a plus 10h minus 1.86 a squared minus 3.72 ah minus 1.86 h squared. Wow, a lot of stuff there. But then I got to subtract h of a. So let's squeeze that in there. So I'm going to subtract h of a, which is up here, 10a minus 1.86 a squared. Now for the problems like this that I have you do in this class, this second term should cancel out completely. Let's see if that holds true in this particular case. I've got a 10a here minus 10a here. Those cancel. What else do I got? I've got a minus 1.86a squared here. Minus and a minus becomes a plus. So the plus 1.86a squared here, a a minus 1.868 squared there. Those both cancel. Look for that to happen for the polynomial type problems that we do like this in this course. All right. So let's keep going. The next thing is to find the slope. So I want delta y over delta x, or in this case, delta y over h. So what's left? This is going to be left 10h minus 3.72 ah minus 1.86 h squared. That's my delta y. That's going to go up here. 10h minus 3.72 ah minus 1.86 h squared over h. So this expression is going to be the slope of the line between the 2 points. It's going to be the slope of the secant line. Do I need to go through all the gory details, or can I just cancel out the h from everything and be done with it? Cancel it all? All right, that's good. What's that going to leave me with? 10 minus 3.72a. Perfect. Perfect. So that's my delta y. So I'm pretty much done, except one last thing. I got to take the limit. So I've calculated this right here. I've got the slope of the secant line between 2 points. Now I'm going to let h get really, really small, and that secant line, the slope of the secant line, is going to become the slope of the tangent line. So the last step here is take the limit as h approaches 0 of delta y over h. So it's going to be the limit as h approaches 0 of 10 minus 3.72a minus 1.86h. And what's that limit going to equal? Yeah, thanks. 10 minus 3.72a. If h is 0, there's nothing wrong with just plugging in the value of h to evaluate the limit. It doesn't create any problems. The first thing you should be trying when you're evaluating limits on your exams is try plugging it in. There's going to be a couple for which it's just going to work. It's like all you got to do is plug it in, and you'll be really happy. So this, I'm going to call it as h prime of a. It's also the slope of the tangent line at any particular point. We'll call it h prime of a. The nice thing, like I said, is that that tells you the slope of the tangent line for any value of a that you choose. So let's think back here. Last time we ended up with finding the slope of the tangent line when a equals 1. Here, that means just plugging in a equal 1. So h prime of 1 would be 10 minus 3.72 times 1, so 6.28. Okay, that's nice. But what's even nicer is that if I wanted to find the slope of the tangent line at another point, say 2, I don't have to redo everything. I can just say, okay, let's find the slope of the tangent line at 2. So 10 minus 3.72 times 2. It's going to be what, 2.56? And the units here would be meters per second. It's nice. You can get the slope of the tangent line anywhere from here. If you take a look at this graphically, and I'll do it on the graphing calculator. So our function was 10x minus 1.86x squared. I know the problem is written with a t, but it's easier just to use x on my calculator. Let me set up the window between, say, 0 and 6. 0 and 6. That should be pretty good. Now, I'm not sure exactly where to set the y coordinates on this, so we'll just kind of guess. Or if you don't feel like guessing, you can hit zoom 0, unless your calculator figure it out for you. There we go. Not too bad. So you can see that the rock or whatever it is that's moving up from the surface of Mars goes up and then comes back down. At some point, it changes direction, it changes sign. So if I looked at the derivative, say at x equal 4, I should see that it's coming down. And what would reflect that it's coming down? What would you see in terms of the sign of the derivative? It should be negative, right? If you calculate h of 4, all right, that's going to be someplace close to 15. 10 minus something close to 15 is going to be negative. So it does reflect what we're looking for. Question? Yeah, please. Yeah. So part B asked you to do it not for a specific value. So the other day we did it for a specific value of, what was it, t equal 1. So the other day we did it for t equal 1. But if I wanted to ask you a question about t equal 2, you'd have to do this all over again. It'd be a real pain. But what we did was we did it for a general value, called it a. And said, okay, we'll just do it for this general value. And now when I get down to the end here, I've got this function that'll tell me what the slope of the tangent line is, whatever value I want to choose for a. So I did it for 1, and I got 6.28, which matches the 6.28 that we got here. If I want to do it for 2, hey, that's real easy. So you've got this. So it's nice. We're moving from doing it for a specific point to doing it for a general point. And moving from the slope of the tangent line to having the derivative function. The derivative function is going to tell you what the slope of the tangent line is anywhere. And so that's nice to have that. That's where we're moving. All right, appreciate the question. Good one. Anything else on this first kind of intro example here? Sound good? Tierney? What's bothering you? Go ahead. All right. Okay. All right. But if you got some questions, please let me know. All right. So let's try this process again of trying to find the slope of the tangent line to these functions. And let me give you a couple quick reminders about finding or working with the equations of lines. So reminders. Yeah. Try that again. There we go. Reminders. RE lines. There's two equations or formulas that I would think and hope that you know. But let me just remind you of them real quick. And that is y equals mx plus b, and y minus y1 equals, anyone finish it for me? M times x minus x1. Good, thank you. So this one, if you have the slope and the y-intercept, then hey, you got the equation of a line. Here, you need two things. You need the slope, and then x1, y1 is a point on your line. And if you have these two things, you can come up with the equation of a line. So, okay. Quite often in this course, we're going to be looking for the equation of a tangent line. So, these things are handy to have around. And we'll start with problem number 20, which is kind of a friendly one, I hope. Problem number 20. And I'll just write it down here for you. Find the equation of a tangent line to the graph of g of x at x equal 5, given that g of 5 equals negative 3, and g prime of 5 is 4. Okay. Well, let's take a moment and understand exactly what we're being given here in this problem. The first thing that you're given is right here. Basically, you got an x and y coordinate. What are my x and y coordinates here that I could put in like a little table? 5 and negative 3. At x equal 5, the function is negative 3. And this also tells me something very helpful. This is the derivative of g. And the derivative of g at 5 tells me the slope of the tangent line at that point. So, cool. I've got my point. So my point is 5, negative 3. That's your x and y, or x1, y1. And then I got my slope. Slope of the tangent line there is 4. So if I want the equation of the tangent line, then I'll just put all these things together. Now there's a couple ways you can do it. You can put everything in and solve for b. I just kind of like putting things in here, but whatever way works for you. So for myself, y minus negative 3 equals 4 times x minus 5. So let's just plug everything in here. So you've got the y minus negative 3 equals x minus 5. And then our slope was 4. Let's clean this all up. Y plus 3 equals 4x minus 20. So y equals 4x minus 23. That's the equation of your tangent line. Not too bad. How are we looking on problem number 20 there? That one okay? All right. The big thing to keep in mind when you're working with these things is this. The slope of the tangent line is going to equal g prime of x, which is the derivative of g with respect to x. The derivative of g with respect to x. And the derivative function is going to tell you the slope of the tangent line at any point. And that's kind of nice to have around. Now we'll look at the derivative function, or we'll look at another one kind of like this. This guy's going to think a little bit more. And that's going to be problem number 24. And let's see, 1, 2. All right. So let's move on to problem number 24. Let me share with you all the information that's given to you in problem number 24. You're going to be asked to sketch the graph of g, and you're given this information. G of 0 equals g of 2 equals g of 4 equals 0. Put another way, if you had a t-table for these points, it would look like this. 0, 2, and 4 would be 0, 0, and 0. You've got 3 points that are right on the x-axis. Okay, that's fine. We can work with that. Let me draw in 3 such points. 1, 2, 3. We'll try and draw ourselves a function that matches some of this. Now I got to give you some more information here. Like they talk about the derivatives. So the extra information there is going to contain this, that g prime of 0 is 1, g prime of 4 is 1, and g prime of 2 is negative 1. Okay. And there's one other bonus piece of information, and that is some information about the limits. The limit of this graph as x approaches infinity of g of x is positive infinity. Eventually this graph takes off towards positive infinity. It grows and grows and grows. The limit as x approaches infinity of g of x, negative infinity of g of x is negative infinity. So on the other side of things, this one just goes down, 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 farther and farther south towards negative infinity. Let's start out with these. These tell you the slope of the tangent line at these points. So the slope of the tangent line at x equals 0 is going to be 1. What's a line look like that has a slope of 1? Anyone? It's going to be at what kind of an angle? Yeah, it's going to be about a 45-degree angle, right? That's going to have a slope of 1. So I'm going to have something. So the function is, at least at 0, is doing this. It's increasing with a slope of 1. And the same thing's true over here at 4. It's increasing with a slope of 1. Or at that point, it has the tangent line has a slope of 1. Now we got to deal with another point. Slope of the tangent line here is negative 1. So it's going to be kind of opposite of that. So something like that. Now we got to pull all this information together and see if we can't form ourselves a graph. So let's start with this stuff in between here. You're going to have a function that's increasing for a little while, but then it's going to come back down and touch the x-axis, and then it's going to decrease, and then it's going to come back up and touch the x-axis. I can't say that. X-axis. The horizontal line, right? There you go. Y equals 0. All right. So see if you can't come up with a way to sketch something like that. This should look like a familiar figure. Well, it has to look like this a little bit. It's increasing, but then it has to come back down to 0, like that, right? Because it touches the x-axis at 2 and again at 4. So, okay, it's got to come back down. Then what happens? Well, it's decreasing for a little ways, but then it's got to change course, come back up here, so that it's increasing. Now let's take a look at this part right here. Where should I draw the line after I cross x equals 4? Should I settle out towards 0? Should I go down to negative infinity? What should I do? Keep going up. This is going towards positive infinity, right? That's what this is saying. The limit is positive infinity. Lou, how about this one? What should I do when I hit 0? Where should the graph go? Yeah, down towards negative infinity. Does that cover all my needs here? I think so. Let's see. The function passes through these 3 points, my x-intercepts. It's increasing here with, roughly a slope of 1, then roughly a slope of -1, then slope of 1, and it has the proper limits towards infinity and negative infinity. So I think that kind of covers everything that you're looking for. Now, could you draw something a little bit different? Absolutely. So that's kind of like the real joy for me in grading these things, is that I have to really actually think. And if you think I mean actual joy, go back and listen to the transcripts, because I don't. It's hard to grade these things because everyone does things a little different, and that's fine. I will take the time to grade them. I had a good question from my morning class, and that was, so with this problem, let me see if I've got this one here. So I don't, let's see, is it here? I think it's here. Let me just shut this off and scroll down. Yeah, so with this problem, here's our points right there, and then you can draw something in here like that. So it's kind of like a sine function in between there. And then to the right of it and to the left of it, you have things going off towards positive and negative infinity. But is there anything wrong with this right here? Not really. It's still going off towards infinity. The only difference is that the way this is drawn, it's not a continuous function, right? It has a jump discontinuity here, but there's nothing wrong with that. So, that's a possibility as well. It doesn't have to be like that, but it could be. Okay, let me come back here. Anything else on problem number 24? Let's take a look at problem number 16. And I'm hoping that everyone got the handout. Yes. So we have kind of pretty much all of what we need here. There's a link online to the Desmos page for this. But let me explain what we're trying to do here. We've got a function, and they want us to find the average rate of change of this function over several intervals. So let me get to the page here in the notes. First thing they want us to do is find the average rate of change of the function between 4 and 8. So first part, we're looking for the average rate of change between 4 and 8. I'm thinking we can do this one visually. Let's see if we can't do that. So what is it that measures the average rate of change? Yeah, the slope. And if we want the slope of a line between 4 and 8, I'm hoping that no one in this classroom actually has to calculate that directly. What's the slope of that line? 0. Yeah, just a big goose egg. M equals 0. Nice. So eventually what we're trying to do is trying to see if there's a way to approximate the slope of the tangent line at x equal 8. So they ask you to calculate the slope of a line between a couple other things here. There's 3 different ways that we're going to do this. So part 2, we're going to look at the slope of the tangent line between 6 and 8. Now between 6 and 8, that's going to be m is 7, 7 minus 5 over 8 minus 6 gives me a slope of 1. So let me draw that line in there for us. Let's see, let's use green here for this one. Between 6 and 8, that's this one right here. for that, we got m equals 1. Two more. For part 3, we want to find the slope of a line between 8 and 10. So between 8 and 10. That'd be this one here, between 8 and 10. So that calculation is going to look like this. 13 minus 7 over 10 minus 8 gives me 6 over 2, which is 3. So m equals 3. Okay. There's one more that we'll try. One more swing at the plate here for us in terms of finding the slope of, or at least estimating the slope of the tangent line here, and that's these two right here, between 8 and 12. So that last one, let's see, I'm kind of running out of colors here. Let's see, we'll try it in red, I guess. Alright, this doesn't show up too good on the projector, but I think it'll show up better at home on the YouTube video. So, these two. And that last calculation is going to look like this. 23 minus 7. So m equals 23 minus 7 over 12 minus 8. So 16 over 4 is 4. So the slope of this line is 4. So we got several different estimates of the slope of the tangent line. Which one do you think is best? 0, 1, 3, or 4? Which one do you think is closest to the slope of this line right here? We'll tell you what. Let me help you look at it a different way. Shut these off. And shut these off. There we go. Let's turn on this graph. And these points. There we go. So we had 4 different lines that we worked with. And let's put in the tangent line. Here's the equation of the tangent line. So, did our first slope, is that a good approximation to the slope of the tangent line? No, not really. How about the second one? Actually, you know what? We didn't do that one. All right. The third one, it's not too bad. Or the fourth one. Yeah, the third one looks closest. Third one, we got a slope of 3. Fourth one, we got a slope of 4. The actual slope of the tangent line, you can see right here, is 2. So the second one's the closest. Worked out pretty good. But the slope of the tangent line is telling you how that function is changing at that instant. And I want to use that to look at another problem. Let's see. We'll do problem number 18 unless there's some more comments or thoughts on this one. All right. Let's finish this up with problem number 18. So it asks us to find the average rate of change of the function on the interval 20 to 60. I'm hoping that you're getting comfortable with average rate of change versus instantaneous rate of change. Average rate of change is the slope of the secant line. All right, it's just the slope of a line between the 2 points. So in this case, between 20 and 60, yeah, about here and about here. So kind of guesstimating based on the graph, I'd say we're looking at points like 20 and 300 and 60 and 700. So we can find the slope of a line between those 2 points. This is part A. And that calculation should be pretty familiar. Anyone beat me on this one? I'm getting a slope of 10. So that's how it's changing on average. But that changing on average really hides a lot of things, right? It hides the fact that for a while the function is actually decreasing, and that here it kind of bottoms out, and then it starts increasing rather quickly. So a lot of times we want to know the instantaneous rate of change of the function, and that's given to us by the derivative. But let's finish up with one more here. It says identify an interval on which the average rate of change of the function is 0. So what's that going to mean? Nice. So a quick one here from Evelyn, 10 to 50. So right here and right here, the function is at 400 for both points. So the average rate of change here would be 0. You could also get an average rate of change of 0 up here someplace if you wanted to, with the appropriate interval here. Any horizontal line that intersects this little hump here twice is going to have an average rate of change of 0. So, okay, let me give you some homework. Where'd it go? So for homework, thank you. Homework, try problems 5, 13, 17, 21 through 25, 31, and 37. That doesn't sound like much. You got a whole weekend. You want a few more? You sure? All right, I don't want any complaints on rating my professor. He never assigned homework, man. It was just terrible. All right, there you go. Good luck with that one.